Hi everyone, we're on chapter 6, the terrestrial planets. This stuff gets very interesting now because you begin to see how the entire solar system formed and the beautiful design of the whole thing. So let's get into it a bit more. We're going to be talking about all of these terrestrial planets that are around in our neighborhood, and in talking about them, we're going to be comparing them for their structure, and we're going to be comparing them for their atmosphere and the possibility of having water and life on those planets. So let's get into it. The solar system, as we know it, is, as you know, mostly empty space. And what you may not realize is that it is flat and disc-shaped, much like the Milky Way galaxy is. So our solar system is a very small part of the Milky Way galaxy, and it has the same flat disc shape to it as the Milky Way. And in fact, you can see there from that side view, what is really interesting is that all of the planets are on very nearly the same plane, which makes it the disk shape. And what I was pointing out to you the other night is the ecliptic, which we have talked about in the past as the shadow of the Earth on the celestial sphere. Well, now you can understand that was an elementary way of looking at the Earth. And the value of the ecliptic is that it is the plane that all of the planets in the solar system revolve around the sun on this plane. So right now, you can see this plane really beautifully in the sky because Jupiter, Saturn, and Mars are really lined up on the ecliptic very well at the beginning of the night. So I hope you get a chance to see that. Kinds of planets. The solar system has two kinds of planets, terrestrial and Jovian. And let's explain that a little bit more. Terra in Latin is the word for earth or soil. And so we call the planets that are like the Earth terrestrial. And some of the other adjectives that you can use for those planets are that they're small, they're dense, they're rocky, they're metallic. But they're very different from the Jovian planets, which are the Latin derivative for Jupiter. Jovian is the Latin derivative for Jupiter. And we'll talk about those in the next chapter, but they're known for their large diameter and their very low density because they're mostly gaseous planets. And let's go into a bit more about our terrestrial planets that are in our neighborhood. We call them small because their diameter is small. And you see there that it goes anywhere from 2,400 for Mercury up to Earth is the largest in the neighborhood. It's 6,400 kilometers for a diameter. And we call it dense because as you see there, that is kilograms per meter cube or cubic meter. And that's pretty dense neighborhood in there. So we wonder why they're so dense, and part of why they're so dense is that they are rocky and metallic. Let's look at that. When we talk about rocky and metallic, this is a NASA and JPL, Jet Propulsion Laboratory, illustration of what that means. In this neighborhood, these planets have something very important in common. They have a structure of a crust, a mantle, and a core. Crust is obviously on the outside. The mantle is a very dense layer between the crust and the core. So let's explore that a little bit more. Generally, the core is metallic, and that's related to the first stage of planetary evolution, which we'll get into a little bit more. But that first stage is called differentiation, and it's differentiating by density, so that The crust on the outside is the lightest density material, and the core is the densest material, like dense is deep. That core for each of these planets is generally nickel or iron. We know most about our core because we can really look at seismographic data from earthquakes in our very active planet, so that we can't go into the core, but we can run a lot of sonar data through during seismic events. And our mantle is between the core and the crust, and the mantle is generally dense rock and metal oxides. We note those oxides from volcanic eruptions from that mantle in our very active planet on Earth. Not all planets in this terrestrial group are as active as the Earth. And in terms of magnetic activity, for the Earth, the liquid core in yellow, the liquid iron core that surrounds the solid iron core, can be combined with a relatively fast rotation at 24 hours to produce a magnetic field and the electric current that always goes with magnetic field, as you learned with electromagnetic waves. So we've got a magnetic field around us, and it has a very specific purpose of protecting us from the sun and the solar wind, which could be very destructive to life on our planet. So we are geared with our electric field to repel the solar wind and to produce a more balanced environment for the Earth. And what about other planets in this grouping and electrical and magnetic fields? No, they don't exist. Venus and Mercury do have liquid iron cores. So that's one step toward a magnetic field, but both of them have such slow rotations that nothing's really moving in that magnetic core to get a magnetic field set up. And when you look at Mars, Mars has no liquid iron core at all. We're going to go into this a little bit more, but as a result, Mars has no magnetic field either. When we talk about these slow rotation of Mercury and Venus, it's very interesting, at least to me, that these two planets, Mercury and Venus, are known for their slow rotations. And they are also two planets that are basically upright in their axis. Now, you combine that with a few things, and Venus not only rotates slowly and not only has an upright axis, but also rotates clockwise instead of counterclockwise, which is really every other planet in the solar system rotates counterclockwise, and the solar system itself rotates counterclockwise around the galaxy. So, and all of these planets in our solar system revolve counterclockwise. So to have Venus rotate clockwise just is such an aberration, and it's been the subject of debate for many years, and it's still not solved. But one of the theories of why Venus rotates clockwise, and it seems to make a lot of sense, is that Venus was in a massive collision billions of years ago that basically stopped its rotation. And now you know from Newton's first law that every body in motion stays in motion unless it has a force against it. You can see that might be the reason that Venus stopped and then started going clockwise, or was spun clockwise. But that entire that is just theories, And there is nothing that tells us why Venus rotates in the opposite direction to everything literally in the galaxy. Very strange. And we will talk more next.